Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on aside as we jump into Chapter 6 in the Big Ideas Math Integrated Math 3 textbook. This is on rational functions. Now, if you don't know what those are, that's okay. We're going to introduce it to you slowly in Section 6.1 on inverse variation. And then we graph rational functions, which I guess is... they build you into it pretty fast, but we've done some transformations before, so I think we're going to get it. And then 6.3 to 6.5 is what I think of when I think of rational functions with regard to the algebra that we do. Multiply, divide, add, subtract, and solve. But we do start with inverse variation here on section 6.1, which is admittedly not what I think of with rational functions, but they are rational functions. Now, the little catch to this section is, because I did some research beforehand and said, if they're talking about inverse variation now, then surely you learn direct variation at some point. But it wasn't in this book. And I've recorded IM2 and IM1 videos as well. It's not in those books either. So where was direct variation taught? Back in Big Ideas Math, grade 7. Consider that to be 5 years removed from what you're doing now. So not that it's a difficult thing to catch up on, but I think that they're kind of in the way of going like, hey guys, remember this thing from 5 years ago? Yeah, we're going to bring it back and do inverse variation. Interesting way of them talking about it. But that's what I'm here for. So, excuse me, if you'd like to jump to the description section down below and download the PDF of this particular section as well as the problem set and find the timestamps for the solution guide video up to all 33 problems for this problem set, you can find that down below, as well as the IM3 playlist. I'm going to begin with the lecture portion. Without further ado, let's go ahead and get started. We are going to classify direct and inverse variation. Remember, direct variation was taught so long ago. Inverse variation is taught so now. And write inverse variation equations. This is, after all, an inverse variation, and inverse variation is an example of rational functions. You can see this is the new vocab, whereas there's some old vocab from before with some other phrasing that we're going to be using quite often. They're saying it right here. You've learned two variables x and y show direct variation when y equals a times x for some non-zero constant a. To explore that a little bit more, with a being a constant value, if I divided both sides by x, you could tell exactly what a comes from, doing y divided by x. So there is the constant for direct variation. Now, inverse variation is kind of an opposite effect here. See, in direct variation, as x increases, so does y. Heck, as x is 0, y is 0. That's how direct variation works. Inverse variation is a way of saying as x increases, y decreases. When you divide by larger numbers, y gets smaller. And x can't be 0. If x was 0, y wouldn't exist, and kind of a vice versa effect. So that being said, this is inverse variation. A can't be 0 as well in this scenario. It couldn't in the top one. And just as I rewrote the previous one, a is a constant when multiplying x with y in inverse variation. Okay, so it is called the constant of variation. Either way, I suppose it would have been called a constant of variation even in the direct variation sets, but I guess they need to revisit that or introduce that for the first time here. And let's go ahead and classify when we have inverse versus direct variation or neither. This example 1, parts A, B, C, tell whether they show direct, inverse, or neither. This one does have a constant with the product, but to hit it home a little bit more, if we get y by itself by dividing both sides by x, you can see an example of inverse variation right there. That's the y equals a over x scenario. So x minus 4, subtraction and addition aren't concepts of variation. It's the multiplication and division aspects that we're really looking for. This is a neither case. It's a linear function, but it doesn't make it direct variation just because. This is a neither case when you get y by itself, as it is by itself. This next one, getting y by itself, means you multiply both sides by 2. And you get y equals 2x. Sum a times x is an example of direct variation there. So inverse variation on top, direct variation on bottom. There's some more examples there. Let's see what else they want to bring up. It says the general equation, I said it too early, I'm sorry. The general equation y equals a times x for direct variation can be rewritten as y over x equals a. So that means, again, getting a by itself, you're dividing y and x. That's what keeps it the constant. And then if you multiply both sides by x in this scenario, then you get x times y equals a, is where the constant is in inverse variation. So I spoke too soon on it. That's okay. We're moving into it. So we have some examples with tables. They say, tell whether x and y show direct variation, inverse variation, or neither. Remember, these x, y tables mean for this x we get this y, for this x we get this y, etc. So we're probably going to have to do some tests. Let's multiply x with y, and let's divide, x from y. and let's figure out if either of those sets are constant. If one of them is constant, then we can represent variation in that way. For example, they multiply x with y here. 2 times negative 12, boom. 4 times negative 6, 6 times negative 4, and 8 times negative 3. Because the products are constant, this is an example of inverse variation. It's also an example of a rational function. Not that we're plotting these points, but you'll see what these graphs look like over time when we do a little bit more of it. But this is inverse variation for part A. Part B, we multiply 1 by 2 and get 2, 2 by 4 and get 8. Well, those are different. Let me move myself a little bit. Those are different, so already, and that's probably what I'm going to do in the problems when we test them, already I can tell it's not inverse variation because the products aren't constant. Try 2 divided by 1, that's 2. 4 divided by 2 is 2. 8 divided by 3 is not 2. 16 divided by 4 isn't 2 either. So they're showing the same thing. 2, 2, 8/3, and 4. Not direct variation either. This is a neither nor case. Neither direct variation nor inverse variation. So inverse, direct, which I know looks opposite of what we see. Inverse is division in the actual problem's sake, but when we're talking about the constant, we multiply our two variables, and vice versa for direct. Writing inverse variation equations. The variables x and y vary inversely, I should say. So we set up this scenario right here already, and we got to find the constant of variation. They say y equals 4 when x equals 3. So we substitute 4 for y, 3 for x, find the constant of variation by, well, multiplying that x with y. Right? So there's the constant. So this ends up being our equation for the inverse variation. And then they say, find y when x equals negative 2. So it's literally, it's just a way of finding the constant of variation, doing a substitution after, and we get our value out from that. This is the only equation we can make when it varies inversely, and y equals 4 when x equals 3. So that's how we make the equations off of that. Here's another set, but a word problem. The time in hours, t, that it takes a group of volunteers to build a playground varies inversely with the number n of volunteers. That means that t equals a over n, or n equals a over t. There's an inverse variation with that, right? It takes a group of 10 volunteers 8 hours to build the playground. It says make a table showing the time it would take to build the playground when the number of volunteers is 15, 20, 25, and 30. This is after you find out the constant variation for this equation. And then what happens to the time it takes to build the playground as the number of volunteers increases? Well, we should already know that answer based on inverse variation and based off logic. You get more volunteers, it should take less time. But we'll see that based on the table, obviously, as well. So, probably things, again, I spoke too soon about, but maybe not either. This is kind of how rational functions work. So we're going to come up with an equation. Here's our mold for that equation. It says t equals a over n. T is the amount of time it takes. N is the number of volunteers. They vary inversely. A is the constant of variation that we need to discover by saying it takes 8 hours for 10 volunteers to build a playground. So when you multiply both sides by 10, your constant of variation is 80. So this ends up being our equation that we use so we can find out how long it would take in each setup for a certain number of volunteers. 80 divided by n number of volunteers is how long it's going to take. So 80 divided by 15 is, I guess this is represented in hours for t. It's, 5.3 repeating. 5 hours, 20 minutes. 80 over 20 is 4. 80 over 25 is 3.2. And 80 over 30 is 2.6 repeating. But, you get 2 hours, 40 minutes. So you can see you get more volunteers as that increases. It takes less time. It's not a linear amount of less time. It's not like another 5 volunteers is another 2 hours less. That's not how it works. This is a curve that's going to do that. That's how inverse variation goes. But we'll see more of those when we graph in section 6 too. But you can see as the number of volunteers increases, the time it takes to build the playground decreases. And that should always be the answer for inverse variation questions. Whereas direct variation questions both would increase together, which wouldn't make sense for this kind of problem. Obviously, we would do a different kind of problem for that. Like the amount of gas you put in your tank, the more money you spend. Obviously, a different kind of question. All right. I think that's all we have to talk about there. And that's actually it for the lecture portion. Let's move on to the vocabulary and core concept check. Number 1 on vocabulary says, explain how direct variation equations and inverse variation equations are different. Well, direct variation equations, its constant of variation is discovered by dividing your two variables, y and x. In inverse variation, its constant of variation is discovered by multiplying your two variables here, finding their product. So I'm just stating it out loud as I write that answer. Number 2, different words, same question. Which is different? Find both answers. What is an inverse variation equation relating x and y with a equals 4? Well, I guess that setup would be y equals 4 over x, given that it's inverse variation. That's part A. Not part A, but answer type A. What is an equation for which the ratios y over x are constant and a equals 4? Well, y over x equals 4. If you multiply both sides by x, that's y equals 4x. 4 times x is direct variation. That seems to be different from the inverse one here. Next one says, what is an equation for which y varies inversely with x and a equals 4? That should be the same as this one here, so that's also an A, as its inverse variation. And what is an equation for which the products x times y are constant and a equals 4? Seems opposite of this one up here, where if I get y by itself, I divide both sides by x, I get 4 over x. Hey, that looks like all the other inverse variation questions. So B is the different one. That's a direct variation scenario. And keep in mind, I know it looks opposite because we divide here, but they're on the same side of the equation. And here we multiply on the same side of the equation. Otherwise, inverse variation is dividing your constant of variation by your variable, say x. Okay, guys, I'm going to start with the problem set, numbers 3 through 33. No idea how long it'll take. Hopefully, it's a pretty decent, quick intro to. Even though we're not really, listen, they are rational functions without us talking about how we use rational functions in the realm with these problems. But hopefully, we just start thinking of dividing by x a little bit more, shall we? Okay. In exercises 3 through 10, tell whether x and y show direct variation, inverse variation, or neither. They don't say explain, so I won't do too much on the explanation outside of what we've seen. This is an example of inverse variation. I'm just going to write the word inverse as we divide our constant of variation by x when y and x are on opposite sides of the equation. Number 4 has x and y on the same side of the equation. Don't confuse that for direct variation just because there's multiplication. In fact, it's a product of your variables that actually leads to inverse variation by dividing both sides by x. You also get inverse variation in this problem here with 12 as your constant of variation. Number 5 actually has division here, but again, don't confuse it for inverse of variation. Y and x are on the same side of the equation, as if to say if I multiply both sides by x, you now see the constant of variation multiplied by said x, and that is an example of direct variation. On number 6, 4 times x equals y is also y equals 4x. That is textbook direct variation. Already good to go. Just write it that way just so you can see it in full. Direct variation here. So inverse, inverse, direct, direct, no neithers yet. Oh, but we are hitting a neither right now on number 7. Now that we have a sum of values, right, that's not how variation works with respect to the definition and what we're doing with it. When x equals 0, y doesn't equal 0. This ain't direct variation. This is a neither case. You can't get it in that form a times x or a over x. Therefore, we not all the same. And that's the same for number 8 as we have a sum of x and y. Getting y by itself in this equation by getting y by itself in this equation by subtracting x over is just some slope-intercept form equation. It may be linear, but it ain't direct. Also a neither case. Inverse, inverse, direct, direct, neither, neither. Number 9. They're trying to trick you here. I don't think they'll get me. On number 9, they say 8 times y equals x. Now, you could argue direct variation here and now, but let's kind of more so get y by itself, say how is y affected with x. Now, if I divide by 8, I get x over 8, but don't confuse that with inverse variation. As x increases, so does y, and just, you can see this as division. I could see this as multiplication in such a way that you're multiplying by the fraction 1/8. This is 1/8 times x. Your constant variation is a, but this is direct variation, y'all. X and y, if I got x by itself, it'd be y divided by x equals constant, and that's what direct variation does. So don't confuse having a fraction, having a division set there with inverse variation, because x is not in the denominator in that situation. X times y is a constant. That is textbook inverse variation. For us to get this worked out a little bit more, this could be y equals 1 over 5 times x like that, which is still, to us, you're like, what's the a value? Well, it's 1/5. But that still might look weird to people. Listen, let's write the decimal version to truly hit it home. It could be 0.2 over x. There's your a over x being divided on the opposite equation, on the opposite side of the equation with y. That is an example of inverse variation. So hopefully you get good recognition on what these things are. I know I didn't write the word variation. I hope that's okay. That's what we're referring to. In exercises 11 through 14, tell whether x and y show direct variation, inverse variation, or neither. Now, I'll tell you what. They did the example thing where they showed when there's a constant among all values, and that's what we need, among all values, and I'm prepared to use the calculator on some problems like these, where if it remains constant for all sets of the product, well, then it's inverse variation. If it remains constant for all sets of the quotient, then it's direct variation. But once it breaks, just once it breaks, then I can truly say it's neither. But here's the thing. Is this inverse variation? X and y are at their absolute smallest now. As x gets bigger, y gets bigger. Is there any chance, and I'm saying this truthfully, like right now, is there any reason I should try x times y here and x times y here and expect the same answer? The answer to me is no, and I might be taking a shortcut by saying that right now, but I think it's worth making that statement that there's no way that this will be inverse variation. I'll show it this once, but after that, you can do your test for yourself and show it's not going to work. Now, I got to do these calculations still. I'm going to do 12 times 132. 12 times 130. This is in the background. And I get 1584. So for x, y's, I'm getting 1584. And then right here, 18 times 198, well, it's going to be a different number. These numbers are both bigger. Why would they ever be the same? This is 3564. I mean, at that point, I'm done on the inverse train. Those are not the same. Now we can try y over x. This one has potential for being the same. Again, this was an inverse variation test up top. Now we're going to try direct variation on bottom. As x gets bigger, does y get bigger? And by the same, constant of variation. 132 over 12, I should already know is 11. Okay. That one's 11. I believe this number's 11 as well. It would be nice if we get 11 for all these. So 198 over 18. Indeed, 11. Listen, I'm going to try and do these in my head by saying 23 times 10 is 230, plus another 23 is 253. That should be 11. 29 times 10 is 290, plus another 29 is 319. So that should be 11. 34 times 10 is 340, plus another 11, or plus another 34 is 374. So that's also 11. So because these all divide here with a constant variation of 11, this ends up being a direct variation problem. And I don't believe I really needed to do that test for inverse variation because I knew I wouldn't get a constant. I know the book doesn't say that. I know I didn't say it in the lecture portion, but I'm bringing it up now that I'm doing the problems. And I think I want to continue on that train. So if you know what to test to show that it's not that, more power to you. If I'll state it out loud, but I won't do the test if it's an unnecessary one. Okay. And again, if it breaks on the other front, on the one that's worth testing, then I'll stop and I'll say it's in either case. So check this out. X is increasing, Y is increasing. There's no possible way this can be inverse variation again. I'm not going to bother with X over Y, but let's try Y over X. Now I do know, this is me doing some like internal division here, because 1.5 times 10 is 15. Subtract 1.5, you get 9. 9 multiples of 1.5. This would be 9 multiples of this. 4 times 10 is 40. Well, 4 times 9 is 36. You know this. 7.5 times 9 is 70. Times 10 is 75. Minus the 7.5 is 67.5. So that's 9 times. And 10 times 9 is 90. Once again, we have direct variation. I'm dividing this one by that one, but I was doing it without the calculator. So this is, once again, direct variation, because we have a constant of variation by dividing those two. Number 13. It's an inverse variation section. I expect at least one inverse here, and we got to have a neither case, don't we? This might be one of them inverse variation checks, right? This time as x gets bigger, y gets smaller. That's not something direct variation would do, so I'm not going to bother trying y over x. I'm only going to try x times y, and if this one works out by multiplying those two and getting the result, then I have inverse variation. If this doesn't work out, then it's a neither case. 4 times 21 is 84. 6 times 14 is 84. 8 times 10.5 is 84. This is 84, and we got 84. So we have a case of inverse variation by multiplying those two, not direct variation. And then number 14, fingers crossed we get a neither case. I mean, it's more work for me, but, Actually, it's less work for me if it is, because that means I can only test something until it breaks. So fingers crossed we get a neither case. As x increases, y decreases. Its only potential is inverse variation, not direct variation. So we're going to try and multiply them. We try x times y. 4 times 16 is 64, and 5 times 11 is 55. Already, despite the fact that this is 62, 63, and 66, whatever, the moment we see the break, it ain't happening. It's also not going to be direct variation because direct should have x and y increase simultaneously. So this is a neither inverse nor direct variation case. That's my test. Thank you. Thank you very much. Okay. Numbers 15 to 22. We only go up to 33, so... The variables x and y vary inversely. Use the given values to write an equation relating x and y, and then find y when x equals 3. So in each scenario, it is inverse variation. That is what the section is built upon. Remember, our inverse variation setup is looking like this here. Y equals a over x. So we're going to substitute these values for y and x in this problem set. Negative 4 equals a over 5. And we multiply both sides by 5, we get a is negative 20. So our official equation is y equals negative 20 over x. This is our equation for our inverse variation for this setup. Now we're going to use that to solve for y when x equals 3. Y equals negative 20 thirds is that value. Decimal equivalence, negative 6.6 repeating. So not my favorite to look at there. I'm just going to leave it as negative 20 thirds. That's fine. Number 16 says x equals 1 when y equals 9 through inverse variation. So x equals 1, y equals 9. Well, what is a divided by 1? 9 is a divided by 1, so a equals 9. Therefore, our equation is going to be y equals 9 over x. Right? When x is 1, y is 9. When x is 9, y would be 1, actually. But they don't care about that. They care about when x is 3. So y is 9 over 3, which is 3. When x equals 3. I really want to show you the graph equivalence of these, but that's what the next section's all about. But again, it's just this curve nature. As x goes bigger, y gets smaller, but it's in a curvy fashion that it decreases. I wonder if there will be questions. You know, a good kind of inverse variation question is regarding area. I'm sure we're probably going to come up with one of those, but as the width increases, the length has to decrease, things like that. They had a really good one in the lecture portion, whereas the number of volunteers increased, the amount of time it took decreased. I liked that one. X equals negative 3, y equals 8. Once again, whoopsie. Once again, we're setting y equal to a over x. And this is where we multiply by that negative 3. I mean, it's almost worth just stating let's multiply y with x, but I want to show you the setup for which we rewrite this equation here. Negative 24 over x is our equation, our inverse variation equation. So, what about when x is positive 3? What does y become? If x is negative 3 and y is positive 8, well, when x is positive 3, y is negative 8. Yes, sir. Number 18. X is getting pretty big to equal 7 when y equals 2. Y is shrinking at that point, so 2 is a over 7. Therefore, a equals 14. This is an equation that's y equals 14 over x. There's very not much to say in these problems. We're just doing the same thing here. So when x is 3, we divide 14 by 3, and voila, that's what we get. About 4 2/3. Okay. Important for graphs in the future, I suppose. Now, at this point, I think we're seeing them for what they are, and it's probably worth us just mentioning that, hey, a is the product of x and y, right? That hasn't changed from the previous problems when we did the test for constants of variation on inverse variation. So I think at this point, I'm just going to do that. Y equals, or a equals x times y. 3/4 of 28 is 21. So this equation will be y equals 21 over x. Despite the fraction on x, that's still how that works. Now 21 over 3 is 7. And that's the y value when x is 3. And keep in mind that means that it's an ordered pair, 3, 7. Don't forget. Don't lose sight of what it is that you're getting out of that. Number 20. I mean, all these hit fractions, so it's really good that we're talking about products now. So here, let's find a by multiplying, again, x with y. Negative times negative is positive. 4 divided by 4 is 1 times 5 is 5. So our equation will be y equals 5 over x. And boo hiss, we divide 5/3 and we don't get an integer out. Oh well, 5/3 is the answer. One less thing to calculate, right? Number 21. we get x equals negative 12 and y equals negative 1/6. So a is the product of these two for inverse variation. Again, negative times negative is a positive. 12 over 6 is 2. So your equation is y equals 2 over x. This might be my shortest. This video might end up even being shorter than quizzes. Probably not. Not quizzes, like the chapter test and cumulative assessment. Yeah, the quiz reviews. So 2 divided by 3 is 2/3. This might be one of my shorter actual lecture video things. I shouldn't speak too soon, though. We still have 12 more problems to go. Number 22, x equals 5/3 and y equals 7, negative 7. Okay, this one will be a little bit different looking because this doesn't divide cleanly. That being said, we are still multiplying 5/3 with negative 7. And that's negative 35/3. Not the cleanest of appearances. So your equation can look like y equals negative 35 over 3 times x. And that's really, this is how I want to write it. It's still inverse variation despite the fact that there's a negative 3 involved, or a 3 involved. I'm going to place the negative a little more in front that way. Hey, we still substitute 3 for x here. Negative 35 over 3 times 3 is negative 35 over 9. It doesn't reduce. We just leave it like that. Weird looking duck of an answer, but that's what it is. Still a rational function all the same with all that inverse variation in mind. Numbers 23 and 24, they vary inversely, but we have to describe and correct whatever errors going on in relating x and y. The first one, already straight off the bat, we're seeing a direct variation setup of this equation. That's a problem. So on number 23, they set up their equation using direct variation. That is so grade 7. Nice little reprieve and not hearing me talk as I typed. Okay, so let's correct their error. It should be y equals a over x, and we just did a whole bunch of these problems. So this is when x equals 8, y equals 5. So 5 equals a over 8, and again, we're going to multiply by 8. We get 40. So our equation with inverse variation is y equals 40 over x. We're not doing anything with that after. That's just the inverse variation setup for this, given that it's inverse variation. Number 24, they do have a proper inverse variation setup, and look, they go straight toward the product. So I'm not mad for doing that from numbers 19 to 22. So they set it up this way, x equals 5, y is 2, there's 10, but suddenly they made it a product equation here. So their constant of variation is correct. Constant. But they set it up as a direct variation problem in the end. So when they do have an a value of 10, which is right, that a value of 10, you now need to lead that into an inverse variation set where we divide 10 by x, not multiply 10 with x. Excuse me. So there's the correction on 24. Is that it? Okay. Numbers 25 to onward, probably some word problems, some how do you see it, some making an argument, thought-provoking, critical thinking. The number y of songs that can be stored in an MP3 player, you guys don't know what an MP3 player is, varies inversely with the average size x of a song. So you can fit more songs if you have smaller sizes per song. Makes a lot of sense. A certain MP3 player can store 2,500 songs when the average size of a song is 4 megabytes. So number of songs varies inversely with the size of each song, like so. And they say 2,500 songs can be stored if you have 4 megabytes per song. So when we multiply 2,500 by 4, we get 10,000. That's 10,000 song megabytes as a product there. So our equation, it says make a table. I don't know if I was supposed to do anything here. Oh, yeah. So here's our equation. So y equals 10,000 over x. Now it says make a table showing the numbers of songs that will fit on an MP3 player when the average size is 2, 2.5, 3, and 5 megabytes. And these are just different things that we're substituting for x. So 10,000 over any of each of those. So given that equation, we got ourselves a 2, 2.5, 3, and le cinco. Now, 10,000 over 2 is 5,000. This is songs, by the way. Songs. Over 2.5 is 4,000 songs. Divide by 3. Well, it's 3,333. I mean, it's not exact. I mean, I don't know if I should write the decimal, but 3,333 songs, and divide by 5 is 2,000 songs. So those are the different things that we'll get from that. The original was 4 megabytes, and we saw 2,500 songs. It says, what happens to the number of songs as the average song size increases? Well, the number of songs in the MP3 player decrease. As the average song size increases, the number of songs on the MP3 player decreases. Okay, as inverse variation should go. That's really for any question that they're going to ask on inverse variation. I don't know if they're going to ask it over and over, but you got an instance of it there. Number 26, modeling with mathematics. When you stand on snow, the average pressure in pounds per square inch that you can exert on the snow varies inversely with the total area in square inches of the soles of your footwear. Sure, I'm sure I could make sense of it if I understood how that actually works. It crushes it and something about footwear stuff. Suppose the pressure is 0.43 pounds per square inch when you wear the snowshoes shown. Say that 5 times fast. Write an equation that gives P as a function of A, then find the pressure when you wear the boots shown. So there's snowshoes and there are boots. So let's start with the snowshoes. So for snowshoes, hold on, I'm going to do P sub S. Pressure sub S equals A over, now this A is the constant of variation. This A is the area of this guy. This is A sub S. And then there's also a P sub boots. P sub B is a little a over A sub B, like that. So 2 different setups for what we're going to do. Let's start with the first one on snowshoes. 0.43 pounds per square inch. Let's find the constant of variation as we divide that by, 360 square inches. So multiplying both sides by 360, we will get, I have no idea, somewhere around something. So it's 360 times 0.43. 154.8. So 154.8. So your equation is P sub S equals 154.8 all over this A sub S, the area guy right there. So there's one equation for inverse variation regarding snowshoes. The boots area we're talking about is 60. And should be 1/6 of that. So I'm just going to divide this number by 6. And we're getting, then find the pressure when you wear the boots shown. Oh, I got it. Boots are a kind of snowshoe. So what they're saying is when you wear these boots, certain kind of snowshoe, we now use that. So I'm only using this one constant variation. I thought we were doing 2 different equations. So now we find, so don't worry about the P sub S and A sub S stuff. This is just pressure of any snowshoes and then the area of any snowshoes. Boots are a kind of snowshoe. So what is the pressure here for boots when you divide by 60? So let's try that. 154 over 60, 1.8 over 60. And I'm getting 2.58 pounds per square inch. That's how that works, pounds per square inch. Pressure is, and this is exact, 2.58 pounds per square inch. And I'm trying to make sense of that. When you stand, the answer is done. I'm trying to make sense of the logic of the situation. The average pressure you can exert on the snow varies with the total area. So because there's more spread out area, you're not really getting as much crunched down. Imagine that you had like just snowshoes just the size of your foot, right? You get to compress that one part a little more. So if you spread it out, it probably doesn't compress that same amount given the weight distribution, things like that. It varies inversely. I think I understand that a little bit. Number 27, problem solving. Why not? Computer chips are etched into silicon wafers. The table compares the area A in square millimeters of a computer chip with the number C of chips that can be obtained from a silicon wafer. Write a model that gives C as a function of A. Then predict the number of chips per wafer when the area of the chip is 81 square millimeters. Now, they didn't say, unless I missed it, they didn't say whether it's inverse variation or direct variation. My guess will be inverse based on the section. However, I'm really just going to look at as X gets bigger, what happens to Y. Or as A gets bigger, what happens to C. As A gets bigger, C gets smaller. So my guess is a test on inverse variation. We're going to try some A times C values. Now, they should all be the same when they're saying write an equation, write a model. I'm hoping that 58 times 448 is, and I need to write this number because we need to figure out what it is, 25984, that it's going to be the same as all of these ones. And suddenly, I don't think they are. 62 times 424 would end in an 8, wouldn't it? 62 times 424. Well, that's a different number. So I wonder if we make like a, I wonder if the calculator has a regression equation form for this. So this is a different number. I'm getting 2626288. Huh, okay. So let's just keep doing these because this is technically a neither case. Notice these are all swimming around, 25872. These are all swimming around 26,000. I wonder if there's something regarding that I can say. Let's see if this one's about the same. They're all about the same, 26320, but they're not exactly. What did they say? Where's the question? Write a model that gives C as a function of A. So it's a model. It's something that we can do about. Now they said write a model that gives C as a function of A. So like F is a function of X, that kind of thing. So I guess C is your Y, the number of chips based on the area. C of A equals. But we need to find that constant of variation. I don't know. Let me check really quickly. I'm checking my calculator. Let me see if I have rational regression on here. Power regression, logistic, sine. I don't think I do. I'm going to make an executive decision and state that these are all around 26,000. So I'm going to use it in that way for inverse variation here. It's 26,000 over A. I'll just put C of A here. I don't need to do. I'll just put C. I don't need to put C of A. So here's an equation that I can use for listen, it said a model. It said predict. It's not evaluate. Predict the number of chips per wafer when the area of a chip is 81 square millimeters. So when you substitute 81 into there, you're getting about something. Let's see. 26,000. Why isn't there a rational regression? I guess that makes sense. That would be really tough to do with. 320.9. Around 321. 321 what? Chips? Chips per wafer. I didn't do anything in computer engineering, really, so I'm not going to pretend like I know how that exactly looks. I know what computer chips look like, but I don't really know how wafers work. It does make sense when you increase the area, you decrease the number of chips, things like that. This should also be the least amount compared to these other ones, right? I am increasing the area to 81. Now 321 is the smallest number of chips. All right, number 28. How do you see it? Does the graph of f represent inverse variation or direct variation? Explain your reasoning. Notice there's no neither case, and this isn't a neither case. This is actually direct variation. Direct variation, I have a couple things I can state. For one, it is linear. It is linear. As x increases, y increases. And listen, we could test some actual values. How do you see it? To me, is supposed to be less about that kind of thing. And also, as x equals 0, y equals 0. That is something that only direct variation can do. Inverse variation cannot. As x equals 0, y doesn't equal 0 would be an example of non-direct variation. So a linear equation where x and y don't equal 0 would be indirect. Number 29, making an argument. See, I told you that would show up as well as thought-provoking. I told you those would. You have enough money to buy 5 hats for $10 or 10 hats for $5 each. Your friend says the situation represents inverse variation. Is your friend correct? Explain your reasoning. It is. That's just a weird kind of situation. Why more hats, less money? I guess they're cheapo kinds of hats. It's a different store that we're doing it. This is absolutely inverse variation. Now, this is inverse variation for two reasons. I mean, this isn't a how do you see it question, though. As x increases, y decreases is part of what I'm seeing here. This is also the product. The product of the number of hats and their cost per hat, and the cost per hat is a constant. $50. $50 hats, I'll say is a constant 50. But we're multiplying. Well, no, it's a constant $50. That's right. $50. Okay. Number 30. The weight W in pounds of an object varies inversely with the square of the distance d in miles of the object from the center of the Earth. At sea level, hold on, let's start with the beginning part. This says something different a little bit here. First of all, it's inverse variation is W is A over D, but it says it varies inversely with the square of the distance. So this is still inverse variation in this scenario here, but it's squared of the distance. Okay. Okay, it's still solve for A. At sea level, that many miles from the Earth, an astronaut weighs 210 pounds. So, now by the way, weight and mass are two different things. Your mass should be a constant amount. Anywhere in the universe, your weight is kind of based on Earth's gravitational pull here. So, we're dividing A by 3978 squared. So A is going to be, 210 times that number squared. So 210 times 3978 squared is a big number. 332314160. I don't know why it's written so high. Okay, so our equation is W equals that mamma jamma. I don't even know what that is. What? It's 3 billion something divided by d squared. Keep that in mind. It says, how much does the astronaut weigh 200 miles above sea level? Remember, at sea level is also this. So 200 miles above that is an extra 200 on top of that. So 200 plus 3978 is 4178, right? So that many miles from the center of the Earth. So let's find the weight with that, and we are going to square that number. So 332314160 over 4178 squared. And this should be our weight of our astronaut on our Earth. Divided by, I still have the previous number, 4178 squared. I'm getting 190.375, about 190 pounds. 190.4 pounds, something like that. Around 190 pounds of said astronauta. Okay, number 31. And by the way, it should be less weight being farther away. Okay. Number 31. Describe a real-life situation that can be modeled by an inverse variation equation. Okay. Seeing that I don't see one later that was what I was bringing up. I brought one up before. It says something like, it was regarding area. You have, length varies inversely with width. You have a constant amount of square feet of paint. I want to come up with a scenario where I'm not answering the question on the constant of variation. Is that okay that I do? Maybe. I don't think we have to do specific numbers, but basically, as in a constant area situation, say to paint, say to have a constant amount of paint. Okay, let's say I had 100 square feet of paint, right? The of a rectangular object. The length of the object varies inversely with the width. Now, that's true. It varies inversely with the width because as the length increases, the width has to decrease. And it's decreasing by the product needs to be the same. Length times width always needs to equal that area. So that will be the case in a constant area situation. I'd come up with a better example, but I don't want to. No, the example's fine, but like with regard to a specific number set where we could solve it, they didn't ask us to do all that. Number 32 on critical thinking. Suppose x varies inversely with y and y varies inversely with z. How does x vary with z justify your answer? Well, if x varies inversely with y, that means that x times y as a product can equal a, some constant. As y varies inversely with z, y times z would also have to equal some constant. Does it have to be the same constant? No. Let's use a different letter like b, I suppose. So what are they asking? How does x vary with z justify your answer? If I could get y by itself in both equations, probably the way I should have written it in general. So I can get y by itself in both equations. Then I can set these two equal to each other where it says a over x equals b over z, like so. So how does x compare to z? Let's get one of them by themselves. I guess get x by itself. I'm going to rewrite this proportionally so this is on top like that. X right is z over b. It looks like it varies directly with z, but in such a way that they have a weird kind of constant. Multiply both sides by a. X equals a over b times z. So with that constant of variation being a over b times z, that is still a direct variation. A and b are just constants. X varies directly with z, with a constant of variation of a over b. All right. The last question, number 33. Using structure. We'll finish under the hour. To balance the board in the diagram, the distance in feet of each animal from the center of the board must vary inversely with its weight in pounds. To balance the board of the diagram, the distance of each animal. Yeah, the farther away you are, the more you're going to lean on your side if your weight was the same. So you'd have to lighten your animal's weight if you're farther away from the center, from the fulcrum. That works. What is the distance of each animal from the fulcrum? Justify your answer. Let's copy that diagram. I need to make sense of this one. I got to think about this one too. So the cat is d feet away at 7 pounds. And this is an inverse variation set. Its distance, how do they say it? The distance varies inversely with the weight. So distance is a over 7. That works there. Now, if this is 6 feet, then this here is 6 minus d feet, which is still a distance in and of itself. So you subtract that. So 6 minus d also equals a over 14. So these are two different things here. We could solve for a or d first. I don't know which one's kind of preferred. What do they want? The distance of each animal from the fulcrum. I guess we should solve for d first. Multiply both sides by 7 here. So I'll get a is 7d. And if you multiply both sides by 14 here, you get a. It's like a system. A is 14 times 6 is 84. 84 minus 14d. So we can set these two things equal. Add 14 to both sides. And divide both sides by 4. You get d equals 4. So what was the question? What is the distance of each animal? Justify your answer. Well, the distance is 4 for the cat. So listen, I don't even need a, ultimately. I actually didn't need to get the final. I didn't know what they wanted as a whole, but it looks like the cat is 4 feet away, and the dog is 6 minus 4, which is 2 feet away. So there we go. The cat is 4, without needing to know the constant variation, from the fulcrum, and the dog is 2 feet away. My answer is justified with my work. There. So there it is. All right, guys. That was pretty quick. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Listen, I hope you understood this pretty well, but rational functions do a lot more than just a situation where there are rational functions in these ones. Next, we're going to do some things on graphs. I hope we get to start to feel it out, especially in a tableless manner, and then we get to hit the crux of what rational functions really do in algebraic senses with multiplying and dividing, adding and subtracting, and solving them. So, although we dealt with rational functions here, not quite the same as the rest of the chapter is going to look. I just want to make sure you know that. Thank you guys so much. Take care. I'm going to see you in the next one.